So we are going to continue the boundary value problem of ODE. Now is the second types of the boundary condition, where now the boundary condition is no longer a constant value but consists of derivative form. So this procedure, if we have a derivative boundary condition, first step still the same thing. You draw the diagram, and then finds the y0 yn. If a normal boundary condition, y0 is given, yn is given. Now y0 and yn are given in boundary in derivative form. Hence you have extra 2 points, which is y0 and yn. Later on the second order differential equation, you are going to replace using this second derivative using yi plus 1 minus 2yi plus yi minus 1 divided by h squared. First derivative you are going to replace using yi plus 1 minus 2yi minus 1 divided by 2h. And then so you get in the formula in terms of the finite different form. After that, for derivative boundary condition, since you need to find including the y0 and yn, hence you have to substitute the I start from 0 up to n, because y0 is unknown, yn is unknown. So you got extra 2 point that you need to find, which is y0 and yn. So you have an n plus 1 linear system to be solved. So mean after you you solve in the step 2 and step 3, then you will get a system of linear equation with n plus 1, because start from 0 up to n. And then you can similarly you can solve using any suitable method that you have learned in chapter 3. So with this we look at the third example, which is a derivative boundary condition. In this case, you have here, you see, we are going to solve actually this second order differential equation, y double prime plus xy equal to x cube, x cube minus 4 divided by x cube, where the x is from 1 to 2, with the increment h is 0.2. So the first step here, draw the diagram. You have the x from 1, increment is 1.2, 1.4, 1.6, 1.82. And then we discretize x using I here. So this is x node, x number 1, x number 2, x number 3, x number 4, x number 5. Hence you have here, this is y node, y1, y2, y3, y4, y5. Now y node is not given directly. You see here, y prime 1. This is y prime 1. If given y bracket 1, then y node is equal to 4. But this is y prime 1. So you need to solve the y prime 1. This is first derivative. You need to solve it using 3-point central difference. And then you can obtain y node as a one equation. Later on you see at another end point, which is x equal to 2. Also you have a y prime 2. So this one is actually, if without this term you have only, let's say, y bracket 2 equal to 1.5, means y number 5 is 1.5. So that is the first type, which is a normal boundary condition. So mean if y0, y5 is known, then you just find y1, y2, y3, y4. But here y number 5 is is given in terms of derivative form, which is y prime 2. Hence you need to solve y0, y1, y2, y3, y4, y5, which total consists of 6 simultaneous linear equations. There you can solve use, and normally it's a 3 diagonal system that you obtain. So you can either solve it using Gauss Seidel if it satisfies the diagonally dominant. If the matrix A satisfies the diagonally dominant, then you can solve using Gauss Seidel. Otherwise Thomas algorithm or Gauss elimination methods. So this is first step. Second step, you need to find y node. So given y prime 1 equal to 4, 1 is actually x node. So y prime x node equal to 4. y prime x naught can be simplified as y naught prime. Okay, so this one is actually x naught. So this notation we can write it in a simpler form, which is y prime naught equal to 4. And then you find y prime naught using 3-point centra. So you are standing at y naught. You want to find first derivative. So it's like your dy dx. So you take the point ahead, which is y1. So you have the point behind, which is y negative 1. So that's why it means so you have here, if let's say this is I negative 1, so this will be x negative 1, this is y negative 1. So y prime, y prime naught, mean you are standing here. So the first mean this is a first derivative. Y prime naught, y prime is look like your difference of y divide difference of x. So using 3-point centra, so that's why it's y1 minus the point at the back, which is y1 minus y negative 1, divided by, from y0 to y1, you have, this is h, y negative 1 up to y0, you have h, so total divide by 2h. And then you are going to eliminate the y negative 1, because later on you will have, after we plug in here, we have a y negative 1. So you have to express in terms of y negative 1. But before that, eliminate that 2h. So y1 minus y negative 1 will be equal to 8h. So you want to solve for y negative 1. So mean y negative 1 you bring to the other side. 8 times h you bring to the other side. You get y negative 1 will be equal to y1 minus, substitute h is 0.2. So 8 times 0.2 is 1.6. Hence, you get y negative 1 is equal to y1 minus 1.6. So you have the first equations. So far, any questions here? I mean, this is a step 2, find y naught. So you can see if derivative form, you have additional works, compared to if the first type, they directly give you, let's say, y. If the first type they give you y1 equal to 4. 1 is actually at this is x naught. So mean y bracket x naught equal to 4. Or simplify form is y naught equal to 4. Mean this one is the first type. Y naught, equal to 4 is directly given. But here, be careful, this is y prime. So this is what we call derivative boundary condition. So this is derivative boundary condition. So if this type y bracket 1 equal to 4, this is the first type, is what we call just a normal, constant or the normal boundary condition. This is a constant, boundary conditions. And any questions here before we proceed to the third step to find the yn? So n in this case is number 5.
No question, Doctor.
Thank you for the response. And then if no, we continue to find the yn. This is the this should be the third step. This one is a step 3. Find yn. And given y prime 2, minus y2. Use this one to highlight. So now given y prime 2 minus y bracket 2 equal to 1.5, 2 is actually x number 5. So it's y prime bracket x number 5 minus y bracket x 5 equal to 1.5. So this one can be simplified, the notation, y prime 5. So both are equivalents. This one, more, what we call simplified forms, and then y bracket x5 can be written as y subscript 5 equal to 1.5. So again, here y prime 5, you solve using 3-point centra. So mean you want to find first derivative, which is standing at number 5. change it back to the plan. For this one, so mean you have okay, your standard, this is x number 5. So ahead will be x number 6. At the back will be x number 4. So correspond, okay, for each x you have the corresponding y. So this is y number 5. This is y number 6. This is y number 4. So the y prime 5 is like your difference, okay, difference of y divided by difference of x, but using 3-point centra. Okay, so that's why will be y number 6 deduct y number 4 here. So total you have here x4 to x5 is 1h, x5 to x6 okay is another h. So total dx is total is the length is 2h. So that's why you get y number 6 minus y number 4 divided by 2h, okay, minus y number 5 equal to 1.5. Okay, and then eliminate this, divide by 2h, by multiply every term by 2h. So that's why you have y6 minus y number 4 minus 2h y number 5 equal to, okay, 2h multiply y, okay, 1.5. Later on, okay, solve, okay, express y6. So the other two term you bring to, okay, the other side. So you have a y6 equal to y number 4, okay, where the h is 0.2. So minus 2 times 0.2 bring to the other side become positive 0.4 y number 5. Okay, and then this one 1.5 times, okay, this is 1.5 times 0.4. 2h is 0.4. Right. So you have, okay, so you get 0.6 here. So y6k is equal to y4 plus 0.4, y5 plus, okay, 0.6. This is the second equation. Okay, and then step number 4, later on, this is actually step 4, right? Okay, in the finite different form, given this second order differential equation, y double prime plus xy equal to x cubed minus 4 divided by x cubed. So replace the second derivative by yi plus 1 minus 2yi, okay, on minus 2yi plus yi minus 1 divided by h squared. So, okay, so xy discretize it, so we have a xi yi. So, okay, right hand side, so equal to xi cube minus 4 divided by xi cube. And then again, we are going to eliminate the, okay, over h squared, this one, by multiply each term by h squared. So h squared this term. Okay, so the first term we are left yi plus 1 minus 2yi plus yi minus 1. Okay, the second term here, okay, multiply by h squared, which is 0.04. That's why, okay, the second term you get 0.04 xi yi, and then the right hand side multiply by 0.04. Okay, and then you got the expand in, you got 0.04 xi cube minus 4 times 0.04, which is 0.16, so over xi cube. Okay, later on, okay, arrange, okay, from, okay, the term yi minus 1, because it's a, okay, left point, yi the center point, okay, yi plus 1 is the right point. Okay, so the right hand side still maintain. So so you collect the term yi minus 1, okay, is here only one term. Okay, and then this term yi, you got two term, collect it together. So that's why this one positive. So that's why 0.04 xi minus 2. That's why coefficient for yi is actually, okay, 0.04 xi minus 2, which is come here. So yi plus 1 is only one term. So this is a finite different formula that we obtain. And then, okay, so to, okay, so to solve I from where to where is normally you need to refer back to step 1. You need to substitute I from 0 up to 5, because you need to solve y naught up to y5. Okay, so far, any questions? I think the new thing is only extra step is actually the step 2 finds the y naught, and, okay, step number 3 find yn. So in this case it's y number 5. So, and step 4 is similar to the previous constant boundary condition. Okay, after that, then this is the formula that we obtained just now. yi minus 1 plus 0.04 xi minus 2 yi plus yi plus 1 equal to 0.04 xi cube minus 0.16 divided by xi cube. So I from 0 to 5, where you obtain it in step 4. Where the x is actually 1, increment 0.2 up to 2. And this is a coefficient for yi minus 1 is always 1. Coefficient for yi plus 1 also always 1. So in this case, you just need to tabulate coefficient for yi, which is given by the formula 0.04 xi minus 2, and the coefficient for right hand side, which is 0.04 xi cube minus 0.16 over xi cube. So you left only two formula where you can quickly obtain from the table menu in your scientific calculator. Okay, so you can turn on the table menu. So key in the first mean the coefficient for your yi as a function fx. This one key in as a right hand side, key in as gx, where the x this is a starting, this is the ending, the step is 0.2. So fx you have 0.04. Xi is a x in calculator, so minus 2. So make sure you check properly. 0.04 x minus 2. Gx is 0.04 x cube. So minus 0.16, also over x cube. So 0.04 x cube minus 0.16 over x cube. Starting of the x is 1. Hold on, never mind. If 1, 2, 3, 4 is wrong, just I should press down. Minus 2 gx, correct. Starting, and then I should press down. Ending is 2. And then step side is 0.2. 1 to 2 step side is 0.2. So now when x is 1, fx is negative 1.96. Later on the next one is negative 1.952. And then x is 1.4. They have negative 1.944. Then negative 1.936. The last one negative 1.928. The last is negative 1.92. Just now I forgot to say that. Yeah, coefficient yi minus 1 is always 1, because here 1, coefficient for yi plus 1 is 1. And then here this one, when I is 1, you plug in into the term yi minus 1. So 1 minus 1, sorry, I start from 0. So you plug in 0 to yi minus 1. That's why you got the term yi minus 1. Where just now step 1, you already express the term yi minus 1. Later on can be substitute here. So the starting is yi minus 1, because when you plug in I0, 0 minus 1, you got y minus 1. So going down will be increased by 1. So y0, y1, y2, y3, y4. To the right side, because it's your left point, so this center point will be increased by 1. So y0, y1, y2, y3, y4, y5. So from y0 to the right point, will be increased by 1. So y1, y2, y3, y4, y5, y6. This one you replace by the equation 1. This one you replace by equation 2. That's why with derivative boundary condition, you got extra load there, extra job there. And then tabulate the right hand side. we already obtained here. Okay, the right hand side. Okay, the last value 0.3 going up 0.2058 going up 1 2. Okay, look at the value at the bottom 0.1248. Okay, up 0.0505. Okay, up. Okay, is negative 0.0235. Okay, going up negative 0.12. So okay, so we have tabulated all the coefficient for yi minus 1, yi plus 1, and right hand side. Okay, after that, the next step, just now up to step 1, 2, 3, 4. Here. This is step number 4. Okay, let's say this is step 5. Let's say your table here, let's say you can represent your step 5. This is the step 6. Substitute the first boundary condition into the first equation. Okay, into the first equation here. What I mean, first equation here, this one, and the second boundary condition into the last equation mean here. So okay, from the first equation in this in the table, you have 1 y minus 1, so minus 1.96 y naught plus 1 time y1 equal to negative 0.12 here. And then okay, this one is actually from equation 1 that you obtain in step 2. Y negative 1 is equal to y1 minus 1.6. Okay, hence you replace here. Y, okay, negative 1 is actually, okay, you have y1. So mean you plug in this one, you have, before that, maybe from here, you got y1 minus 1.6 minus 1.96 y0 plus y1 equal to negative 0.12. That's why y1 plus y1, y1 plus y1, that's why you got 2y1. So minus 1.96 y0, okay, and then 1.48, okay, 1.48, okay, minus, right? So minus, okay, 1.6. You get negative 0.12. Where's the calculator? And you can go back menu here. Later on, menu number 1. So 1.48 minus, okay, sorry, this one. From here, negative 0.12 plus 1.6. In total, you got actually 2y1 minus 1.96 y0 equal to 1.6 minus 0.12. You obtain 1.48. Yeah. And 1.6 minus 0.12. Okay, 1.48. Okay, so here any question? I mean, from the table, you got the extra term y minus negative 1. We just need to solve y1 up to y5. So y negative 1 is the extra term where you need to eliminate using equation that you obtain from step number 1. Step number 2. Yeah. When you find y0, you obtain y negative 1. So which is equation 1 here. So so from the where is it? I mean, from the equation 1 in the table, you have 1 y minus 1. So y minus 1 you replace by y1 minus 1.6. So y1 minus 1.6 minus 1.96 y0 plus y1. So total is 2y1 minus 1.96 y0 negative 1.6 bring to right hand side, so it becomes positive 1.6 minus 0.12. So you obtain this is actually 2y1 minus 1.96 y0 equal to 1.48. So this is the new equation 1. The new equation 1. Or else you come like this. Later on you come. To be not confuse you, let's say this one we use star, because later on you also got equation 1. And Where is it? This one don't use number 2 because later I confuse with the number 2, okay, of the linear system that you are going to form. This one, let's say we call double star, equation double star. Okay, so now this one, okay, from the equation star, you eliminate y minus 1 from the equation star. So you get this is the latest equation 1. Then this is your equation 2, equation 3, equation 4, equation 5. Later on, here, after you plug in, after you, from the equations, original equation 6, you have 1 y4 minus, from the last one here, you got y4, because 1 y4 minus 1.920 y number 5 plus y6 equal to 0.3. Y6 is actually, this one is the double star equation, the equation double star they obtain in step number 3. Go back. Step number 3 here. Step number 3 here. Y6 equal to y4 plus 0.4, y5 plus 0.6. Let's call it equation double star. Thus you plug in y6 as here. So you got y4 minus 1.920 y number 5 plus y4 plus 0.4 y5 plus 0.6 equal to 0.3. So you have here y4 total is 2y4, and then negative 1.920 plus 0.4, mean this y5 collect together. You have here negative 1.92, negative 1.92, y number 5 add up 0.4, you get negative 1.52 y5. Later on 0.6, you bring to plus 0.6, 0.6 you bring to the other side, so it becomes 0.3 minus 0.6. That's why you get negative 0.3. This is the new equation 6. So mean, equation 1, the new equation 1 is here. Then combine with equation 2, 3, 4, 5, and new equation 6. So you got 6 equations, 6 linear equation. Then put up into the matrix form. You are going to solve y0 up to y5. So you may indicate here, this is column to guide you to key in the coefficient correctly. So y1, y2, this is y3, y number 4, this is y number 5. So this is your matrix A multiply, matrix A, which is a 6 by 6, and vector vector y is actually 6 by 1, and then the result is a 6 by 1 vector B here. This is your vector y from y0, y1, y2, y3, y4, y5. So equal the vector B here. Don't take from the table. The first and the last, you have to take the latest after you plug in boundary condition. So the new equation 1, you got 2y1. Start from y0 first. You have negative 1.96 y0. That's why here, negative 1.96 y0. And then 2y1. You got here 2y1. So 2y1. Equation 1 only have y0, y1. So y2, y3, y4, y5 are 0. Then equal to 1.48. 1.48. Later on, second equation from here. You can read directly 1 y0. So y0, coefficient y0 is 1. Second equation, coefficient for y1, negative 1.952. Coefficient for y2, so y2 is 1. So y3, y4, y5 are 0. Okay, vector b or right hand side, okay, is negative 0.0235. Okay, next go to the third equation. Third equation start from y number 1. So y naught is 0. And their coefficient is 1. Okay, followed by negative 1.944. This is y2. 1, y3. Okay, y4, y5, 0. Right hand side is 0.0515. Okay, next equation 4. Okay, start from y2. So y0, y1, 0. Their coefficient 1, negative 1.9361. Okay, right hand side vector 0.1248. Equation 5. Start, okay, y3 is number 1. So this is y3. So y0, y1, y2, 0. So y3 is 1, 1. Followed by negative 1.928. Y number 5 is 1. Okay, and then right hand side is 0.2058. Okay, later on the last equation here, after you plug in the boundary condition, 2y4. So start from 2y4. So mean y0, y1, y2, y3 are 0. Okay, from here 2y4 minus 1.52, minus 1.52 y number 5 equal to negative, okay, here negative 0.3. So you got, okay, 6 by 6, okay, 6 by 6 system. And then in this case, even though this is 3 diagonal, you can always solve with, I think 3 diagonal you can solve with Thomas method, but it's quite tedious. Okay, and then you cannot solve using Gauss-Seidel because it is not diagonally dominant, because here diagonal value here negative 1.96, okay, but here this value, okay, 2 is greater than magnitude of 1.96. So the second equation also, they are, okay, the second, third, fourth, all are, okay, mean, okay, non-diagonal value and add up is greater than diagonal. So this is not, okay, diagonally dominant. So you cannot solve using Gauss-Seidel. Okay, but you can solve using Gauss elimination method. Okay, up to here, any questions? Okay, so first I'll try to solve using the, okay, inverse matrix method. So I put out the coefficient for, okay, matrix A first. Okay, yeah, negative, okay, 1.9696 2 2 3 4. Okay, let's say this is y naught, y1, yeah, cannot, y3, 1 this is y2, y3, y4, y number 5, y number 6. Okay, so this is a matrix A. This is a, okay, vector y. This is your vector b. So vector b, you have 1.48, and then negative 0.0235, 0.0515, 0.1248. Okay, and then 0.2058, missing one. Okay, b not 1.4x, and then negative 0.0235, 0.0515, 0.1248, or up to y5. So no wonder. Okay, and then, okay, the vector b, the last one is negative 0.3. Okay, now key in the matrix A. So this is okay. The second row coefficient for A is 1 and negative 1.9521 0 0 0. This one 0. The third row 0 1 negative 1.9441 0 0. Okay, the fourth row 0 0 1 negative 1.93610. Okay, the fifth row 0 0 0 1. Oh, maybe I need to enlarge, otherwise you can not see clearer. Okay, sorry. 1 negative 1.9281. So the last row 0 0 0 0 2 negative 1.52. Okay, let's check. Okay, bottom. The diagonal negative 1.96, negative 1.952, negative 1.944. Okay, negative, okay, 1.936, negative 1.928, negative, okay, 1.52. Okay, the below diagonal all are 1 except the bottom. Okay, the last row is 2. Okay, and the first row, okay, on top of diagonal 2, the rest are 1. So here, vector B correct. Okay, try to solve okay, whether we can obtain using inverse metric method in Excel. So the result is a 6 by 1 vector. So make sure it selects the 6 by 1 vector. And then, okay, MMULT to multiply two matrix. Okay, we are going to multiply the inverse. So M inverse. Okay, we are going to okay, inverse of A. So that's why M inverse, I select the range of A. Okay, and then, okay, I multiply with vector B. So close the bracket. So you see MMULT bracket M inverse. Okay, bracket, this is actually range of, okay, your metric A, comma, the vector B. Okay, close the comma, okay, for MMULT.